So, hello everyone. So I'm here back again to let you know the progress in the Arity project. Sources and Natalie are collaborators, and we are sort of working together towards this sort of higher mathematics in a way that I'll make precise in a bit. So I want to focus on ternary structures particularly. I mean, we see Arity as a staircase, and we are all inhabiting the first step, the binary step, and so ternary would be the next step. So that's why I'm so focused on ternary. It's not because I think there's something deeply interesting about ternary as opposed to any other Arity. So I want to give a very concise presentation. I want to be fairly bounded and not to explore too much and sort of ramify too much into other topics. But let me start by the motivation that first led me to this topic. Many of you are very aware of this because I've explained it before, but just for the record, I'd say that my main curiosity stream sort of interest was n-ary Lie algebra integration. So this is, the standard situation where you have a binary Lie algebra. It's very well known, very old classic mathematics, that we have this functor that, taking any Lie algebra, we can find a simply connected Lie group that integrates it. Now the issue is, if you define a 3 Lie algebra to be a vector space with a trilinear, fully antisymmetric trilinear operation that satisfies the generalized Jacobi identity, which is this particular expression here. It might look complicated, but actually when you look at it, it's basically the fact that the adjoint map that you define with, say, x and y blank acts as a derivation of the bracket. It's a very natural condition to impose. So it generalizes to any higher Arity brackets. And so people have studied these algebras with some degree of attention and some degree of, so some classifications have been done, etc. So the natural question is, so if I know that I can do the Lie functor for a binary Lie algebra, can I do a similar kind of construction for a ternary Lie algebra? And the answer is, this is an open problem. Nobody knows, basically. And so this, if you're interested, there's a paper by a friend of mine at Carrara from 2010 that summarizes the whole situation with high Arity Lie algebras and Leibniz algebras and all the business. And they, at the very end of that review paper, they outline this problem that, I mean, they claim that at least 10 years ago, and I would claim that there's not been a change in the last 10 years, that nobody has really even attempted the full integration problem of high Arity Lie algebras, in particular ternary Lie algebras. So the question is then, what is the ternary analog of associativity? One is very naive and just thinks of Lie groups as being this continuous associative objects. Then naively, because we have a fairly well-established theory of ternary Lie algebras, you might think, well, if I just find something that has an analog of ternary associativity, I just put some smooth structure in that object, and that should infinitesimally give me the 3 Lie algebra. That's the hope. That's sort of the sketch of the program that people had in mind. And everyone so far has failed. And not only has failed in a technical sense, but also but further, we don't have candidates for what could be integrators of 3 Lie algebras. That's kind of the mystery part of this entire business. So when one learns category theory, of any of you is a little bit more categorically minded, you know that groups are, within the concept of category theory, they're just very special kinds of categories. So and so if you are trying to generalize associativity and you do take that route, which is, by the way, not the only route that you need to take to generalize the algebras, but if you want to take it, certainly categories are somehow the more minimal context in which associativity lives or is expressed. So before we get into that, so that would be sort of the goal of the program. One of the main goals of the program would be generalizing the notion of categories, conventional categories, into higher Arity. But before that, let me give you a primer on heaps. So out of curiosity, if you could raise your hands or type a +1 in chat or something, I just want to see how many people have heard about heaps before. So heaps are algebraic structures. So this is in the context of algebra. So these are ternary algebraic structures on sets. Who has heard of these objects before? Not from me, because I might have mentioned them in the past. Okay, I see James Boyd, one hand up. So I don't see many hands up. So I imagine not many people. I mean, I did a seminar here at the University of Edinburgh yesterday for the mathematical physics people, and there was a room of about 30 people, and nobody had ever heard of heaps. So let me very briefly tell you about heaps. So first, we begin with semi-heaps for the minimal axiom. So a semi-heap is a set with a ternary operation that satisfies this identity. Now, pay attention to this identity in that left side and right side are just the standard associativity properties, and the middle term is a departure from associativity because D and B are swapped, as you can tell. So this is, by the way, this was introduced by Wagner, a Russian mathematician, in the 40s and 50s. He was, in fact, a differential geometer. I was interested in transition functions and transition of charts in manifolds and things like that. And he was studying partial bijections and sort of relations in sets and so on. And he discovered this sort of structure in that context. So what are the main examples of semi-heaps? Well, the most natural example that one can actually kind of guess just by glancing at the axiom is that of an involuted semigroup. So an involuted semigroup is a set G with a binary operation that is associative and an involution that is an anti-homomorphism. So it reverses the order of the binary operation. So the semi-heap that is defined from any involuted semigroup is the obvious choice there. I mean, A, B star C, you can imagine that when in the above axiom is obvious why it holds, because I mean, the left and right terms are just associativity of the binary operation, and the middle term corresponds to associativity and the fact that the involution is an anti-homomorphism, so it reverses the order of the binary composition. Now, what is the other example? I mean, it's perhaps not such a different example, but it's certainly a very big set of examples, which is dagger categories. So any dagger category, which is a category with a dagger endofunctor, so that's basically a way to send morphisms to another morphism in the opposite direction, has, so the Hom sets in dagger categories, they all carry this semi-heap structure in a very trivial way. So essentially same idea as with involuted semigroups. So what's interesting, and what Wagner proved in 1952, that's the sort of reference that I'm quoting here, is that any semi-heap can in fact be embedded into an involuted semigroup. So semi-heaps somehow don't go beyond standard binary algebraic structures. So in fact, we can go further from this, and this is kind of part of the reason why I wanted to introduce heaps in the first half of the talk, because heaps, although they are ternary structures, they are fairly well understood, and they are non-associative in a strict sense. They are very much still within the binary world of conventional mathematics. So if we introduce the concept of a bi-unit, so that's trying to generalize what a unit or a neutral element is in a conventional binary operation, we think of an element in H that satisfies the following property. So you could have partial bi-units, or left and right bi-units, or lateral bi-units, and so on. But the standard definition that Wagner gave, and the important one for us, is this particular one, which you can see clearly why this is in the examples above. If you have an identity or a neutral element, you clearly see that these would be bi-units. And so the definition of a heap, now coming to the object that we're going to talk about, is that of a semi-heap whose elements are all bi-units. So this is all made by units. So this is actually a pretty strong condition, and the interaction and actually the axiom of bi-units and the axiom of semi-heap interact non-trivially. So you in fact can drop the equalities with the middle term. So this non-associative looking term, you can actually drop that if you assume the heap condition, meaning that you have all elements being bi-units. But anyway, that's not so much the point. So what's interesting about semi-heaps is that if you ever have thought about groupoids, is that if you ever have come across groupoids, or you maybe are aware of group actions, and you have some intuition about group actions, essentially groupoids are a very natural way to generalize group actions. If you're aware with group actions, but not groupoids or not category theory. In category theory, in category theoretic terms, groupoids are super natural. I mean, they are just category G with inversion as an involution or as a dagger in a way. So that means that you're basically taking all your morphisms and their inverses always exist, and by definition, inverses need to be unique, right? So they're kind of very symmetric categories, right? It's the sort of the categorical notion of symmetry. The most general one will be a groupoid. So in the context of groupoids, or in the context of group actions that generalizes directly into the concept of groupoid, you have this notion of an isotropy group, which is effectively all the elements of your group or groupoid that leave your points in your action set unchanged. So in more categorical terms, you'd say that the Hom set of on any given object A of all the maps from A to A, or all the morphisms from A to A with morphism composition. So pictorially, you're thinking of all the arrows from A to A, that forms a group where inversion is inversion because it's a groupoid, and composition is the composition of morphisms, and the identity is just the identity arrow, the identity morphism. So what's interesting that we can see with heaps is that if we now think of two potentially different objects, we can actually define a heap structure on that. So we call that the translation heap, because the picture is that given A, B, two different objects, I can think of all the morphisms between them. And so the heap structure actually captures the algebraic sort of redundancy that there is in the way that you can travel from A to B, right? So in some sense, you can package all that redundancy in a neat algebraic structure. That's what we call a heap. Okay. And by the way, it's the same definition as the heap is the semi-heap for the dagger category. It's just now the dagger is inverse, and therefore, because you're in a groupoid and all your morphisms are invertible, then all your morphisms are biunits in the sense of heap. So that's why these things become a heap. So it actually turns out that the semi-heap, sorry, the heap GAB with this definition of a structure corresponds to the semi-heap that you will get from the isotropy group seen as an involuted semigroup with inverse. So there's that sort of compatibility condition. And then there's also a condition that the semi-heap AB is isomorphic, is canonically isomorphic to the semi-heap BA, effectively because inverse gives you a bijection between Hom sets. And that bijection actually turns out to be a heap homomorphism as well. So this gives a very nice heap picture of groupoids, which effectively puts isotropy groups on top of each object, and then it connects them with heaps of translations. So the sort of graph theoretic statement here would be that a simple undirected component complete graph is a faithful representation of a groupoid when you put groups on your vertices and you put heaps on the edges. So that's it's a nice way to see heaps in a very explicit context. I mean, this is heaps doing some work for us that we might want to capture. I mean, everyone thinks of groupoids as generalizations of I mean, it's very often the way that people, especially in differential geometry, the way people think of groupoids. And it's very nice to have now a sort of an algebraic handle on not only the sort of stabilizer part of the groupoid, the isotropy groups, but also the translation part of the groupoid. When now we bundle all these translations from two objects and they form a heap, right? So it's like a heap of arrows. It's a kind of, the name kind of plays well with that analogy as well. So anyway, so this was some outlook of what heaps are and what they can do for us. Now let me go back to the original motivation of generalizing categories, generalizing the arity of category theory. So there are several approaches that exist, and there's a lot of people that are much more knowledgeable in this, even in this Zoom call, than I am about this. But effectively, all these flavors of polycategories, operads, and higher categories, they all have some way of moving towards sort of involving more than pairs of objects and morphisms between them. You're always trying to sort of go beyond that framework a little bit, but the crucial common denominator of all these approaches to sort of more objects and sort of higher order category theory in some general sense is that they are all constrained by sequentiality. They are always deep down, they're always having some kind of directionality. So you have some collection of objects in polycategories mapping into a collection of objects, or you have in operands, you have several sort of trees that are splicing in that particular way, always sort of corresponding to a particular direction of the composition. And in higher categories, of course, we're just moving to higher morphisms in the sense of morphisms between morphisms between morphisms. But at each step of the way, you're always thinking of arrows. You're always thinking of morphisms as being some kind of input, output, or source and target sort of objects. And so the sort of the punny way of asserting my goal here is to say that we might break free. We must break free from the chains of sequentiality, right? So all these examples are very deeply sequential. They have, in their very definitions, they have a sequential nature, right? So the kind of approach that we like to take in this project is one that was actually indirectly proposed by Topensarov in the 80s and early 90s, when he was effectively recovering or explaining the categorical structure of high arity relations. So he did some work in trying to give some general notes on what could happen when you try to generalize the concept of category into this higher context. But unfortunately, he was not able to really realize actually fully realize this idea. And I think people agree that that program essentially stopped at that point. So we're in some sense picking it up back again, with obviously influences from many other angles. And we hope that we're making some new progress in it. So the main context in which we are starting to probe this higher arity realm is what we call array algebras. And array algebras are actually trying to encompass two very important examples of what people, when we think about operations and compositions and algebraic frameworks, we really are generalizing effectively a couple of examples, one being matrices and the other being relations. So an array is generally some index object with some algebraic structure. So at this point is very vague. So what I mean, if you want to be more precise, is you can have a map from a set of indices into some algebraic structure A. And so you could denote it, like typically you denote any index object with some indices. We would call this an n-ary or an order n array. And if we take A to be a field, for example, or a ring, then, and for example, you take sets that are finite, then we get matrices. So these are, some people would call them tensors. I think that's an incorrect name in general, but that would be the more popular name in sort of computer science circles. And then if you take A to be the Boolean semi-ring of two elements, then with I any sets, then these are n-ary relations. So they cover all the traditional set theoretic relations. So anyway, so for our work, we mostly just assume that A is a semi-ring, because that covers these two examples and gives us enough flexibility and enough generality. So effectively, if you really only worked with matrices or tensors before, then you could think that these are all sort of components of tensors, and you could live happily through all my explanations. So there are many ways in which we can compose these objects with each other. I mean, these are ways effectively determined by the index structure together with the algebraic structure of the value set, of the target set, right? The semi-ring in our case. But we are going to focus on generalizing binary composition. We are actually very, very laser focused on associativity, as I said in the beginning. So we're going to try and take the prime example of an associative structure in this context, and we're going to try and generalize it. So what is binary composition? So if you have a matrix, two matrices, A and B, we learn in kindergarten for the grown-ups here, we learn that matrices are multiplied in this particular way. Now we can similarly make use of this sort of general semi-ring notation to basically write down the composition of relations. Now A, B are binary relations between two sets in effectively the same way, and the algebra works in the same way because the operations are associative and distributive and so on. As I said, only thing that we really require is a semi-ring structure. So diagrammatically, I'm thinking of this one-dimensional line between I and J, and then diagrammatically that came from IP and then PJ, and then having some kind of point of connection, some kind of meet in the middle, right? So this is what motivated what Tyler suggested to call Plex notation when I was visiting him in South Africa a few weeks ago. I mean, Plex, I think, could be interestingly, so it could be a callback to simplex and just dropping the sim part of that word. So effectively, Plex notation tries to depict n arrays by n-1 simplices. So as implied by the previous pictures, will represent sort of dots or single vertices in a hypergraph as vectors, one edges as two arrays, and three edges and so on as three arrays and so on. So basically, the way that we're gonna study composition is by taking contractions. So we're gonna try and generalize this sort of operation, but for arbitrary arity of our or arbitrary order of our arrays. So that means that diagrammatically, we're gonna use these elements. You can think of them as simplices, or you can think of them as hyper edges, and we're gonna place them in a hypergraph, and we're gonna whenever they meet, we're gonna draw this dot, meaning that we're gonna do a contraction. You can do more things. This is not the only thing you can do, but for now, I'll just focus on that for the sake of concreteness. And so the general composition might look, potentially complicated. You have a collection of triangles and a collection of any higher shapes or whatever, and you will form this hypergraphs, and they will tell you how to contract. So we'll see this in exact detail in a second. So this notation is ambiguous in the sequential order of indices, because remember, we did define arrays as something that have a sequential order of indices, and they are ambiguous to capture that order, but they are effective at capturing the compositional topology of the program. So this is something that traditionally in mathematics has not been so problematic, because most operations are very sequentially constrained and are or particularly binary. So compositional topology has never really been sort of a problem or something in people's head, at least explicitly as part of the mathematical formalism itself, like the articulation of the mathematical formalism. So that's kind of what we're trying to do here. That's our main goal, our main step in this program with array algebra is to think about the role of compositional topology, basically. So in particular, we're going to be looking at order preserving compositions, right? So for example, we started with a binary case where we had two arrays that meet one vertex, and that creates a new two array. So that's usual matrix multiplication or composition of relations. But now by the same token, we can just look at the hypergraphs that involve three arrays, and then see which of them give you back a three array. Right? And this is just a matter of combinatorics. There's nothing mysterious going on, but there are plenty of them. In fact, topologically speaking, so meaning the different topologies that you can have, the different hypergraphs that can tell you how to contract the indices. In fact, there are, I think it was 5. And if you actually index things differently, you have 10 different products that are 10 different array operations that are ternary. And that's only using one sequential order. There will be many sequential reorderings of those that they will be formally different as array compositions, but they will all be topologically equivalent. So I just depicted some of them, and then we're gonna look at some of them in particular. But before that, let me talk about identity arrays. So one feature of matrix algebra, the first time you learn some matrix algebra, or when you're doing compositional algebra of relations, you learn that there's always some trivial natural matrices or some trivial natural relations that you should consider. And these are, of course, the identity relations with respect to the composition that we're talking about. And so now we just generalize trivially as higher Kronecker deltas, so to speak. And we depict them by sort of equality, following this sort of category theoretic convention of just equality as a morphism. And so what's nice about these identity arrays, these Kronecker deltas, is that they form a compositional subalgebra under this contraction operation that we've been talking about. And so, you can combine them in many ways, and they will close as a subalgebra. In any possible way that you can contract them, you will get the same, so the correct delta at the order that should be, right? Because I mean, after a contraction, the order of your inputs is gonna change. Sorry, the order of your output is going to be different from the order of the inputs in general. So they are nice compositional subalgebra, and they are compositionally neutral. That's why we call them the identity arrays. That's why we kept the name from the standard terminology. So that means that you can throw them basically in any given hypergraph of representing some contraction for higher arrays. You can throw them whatever. There's a meet, and you have to throw the identity of the correct order for that to make sense, but you can, right? So one comment that I will make here is that some people might be wondering, okay, what are you doing that is not just tensor algebra, right? What are you doing that is not just tensor networks, as they are also known in the literature? The crucial thing that we are doing that goes strictly beyond most of the existing literature on tensor algebra and tensor networks and so on is exactly what's depicted here at in the diagrams at the top right. So you have this triple contraction. It's a three-way contraction of an index. That's something that basically you really struggle to find if you in the tensor literature. By tensor literature, I mean anything from actual multilinear algebra in physics to computer science to all these kinds of things. These are very rare operations that people haven't really looked at that much. So they are definitely part of our story. I mean, you can have arbitrary order of contractions. And so finally, we'd like to make some headway into the question of what is associativity. I mean, this entire story was, can we find a higher form of associativity in this context? And so let's revisit the standard example. This is our guiding example. Is the example of composition of binary relations or the multiplication of matrices. So as a diagram, you would take three matrices or three relations. So in our language, three arrays, A, B, and C, and they will have to share indices in a way that makes them composable. So the usual conformability properties, as they are called in matrix algebra. So the conformability conditions are just that you can basically splice these arrays in this particular diagram. And so the whole sort of idea that we had and we've sort of been developing the last couple of months is, because I mean I was personally very involved in trying to probe for higher Arity associativity, but I was kind of stuck of not having a tool to or some systematic way in which I could make progress or ask questions in this higher Arity universe. And it so happened that by some coincidence, some very fortunate conversations with Tali originally and so on, I was able to think of this confluence property of some rewrite systems which is a kind of a trivial perspective to take on associativity, on traditional binary associativity, but it turns out to be not only non-trivial for higher Arity operations, but I think actually potentially very fruitful, because we don't really have any other offer for a way to probe high Arity associativity. So we begin by a very simple example of confluence, which is the usual binary associativity. So the way this works is I start with a graph, hypergraph in general, that is going to represent some contraction of arrays. In this case, is this ABC graph, and I select a motif that I'm going to detect for. Right, so the motif is effectively the product, right? That's kind of the whole algebraic translation of this. It will be the product. But for now, just think in terms of graphs and motifs, subgraphs, and so on. So when we do motif detection, by the way, these motifs correspond to the product. That's sort of the algebra side of the picture. Then we just do a rewrite system. So you scan for this motif, and when you find one, you rewrite it, and then you do your typical, in this forum at Wolfram Research, I don't have to specify too much. At the physics project, I don't have to specify too much about rewrite systems. That's kind of why I wanted to tell you about this stuff. And so you have this very natural rewrite system, very simple rewrite system. And then the middle stage gives you associativity, gives you binary associativity of the product. So no mysteries here. But what about when we take a different product? So if you remember, one of the order preserving compositions was this bottom shape that looks like a fish, the ABC shape, that we appropriately call the fish product. And the idea is, so how about that shape? So the proposed hypergraph that we begin with is this so-called lungfish, 5 triangles in this particular configuration. And the motif that we're going to detect is the fish. That's kind of what we're trying to do the analogy here. I mean, before we were detecting the binary product, now we're going to detect the ternary product. So just for anyone who's curious, that is the formula that corresponds to the fish product. You can obviously change the order of the indices in equivalent ways, but this is the one that we're looking at here because it's the one that satisfies the correct axiom. So if you really want to go into the array context, that's the product that you should be using. So now we just run the same sort of algorithm. We try to detect for fish, and we find this simple rewrite system. We interestingly notice that the left fish here is just the fish that you see attached on this end. The right fish here is the fish that you see attached on this end, and then the middle fish, interestingly, is a fish that is pointing in the other direction, right? So perhaps some of you is already guessing that what this is showing us is precisely the semi-heap axiom, right? So this is the confluence property of this lungfish hypergraph gives us precisely the semi-heap axiom. So this is what would lead me to claim that semi-heaps or heaps in general, they are not. So people in the literature have called them quasi-associative, para-associative, associative of the second kind, and things like that. So they are well known for being non-associative structures that behave nicely and they're fairly well understood. And my claim would be that actually semi-heaps are as associative as groups, say. It's just that you didn't have the right language to sort of manifest the fact that they were associative in exactly the same way. They correspond to dependently confluent rewrite systems. And I'll make a point about that in the questions later on because I don't want to extend too long. So then the general question still remains. I mean, unfortunately, we haven't. I would love to give you more examples of this dependent confluent that corresponds to some axioms, but unfortunately, we haven't found them yet. And so there's this trio of ternary products of arrays that you can define, and they're particularly interesting. I call them the Holy Trinity because they are 3 and they're ternary, and it's a nice name. And they're special in the 10 possible topologies of ternary products that I mentioned. There are not 10 topologies, the 10 possibilities of products. They're special in that they have all the arrays involved in a symmetric manner. So, for example, the fish, you could push back, and you'd be very right to mention that the fish is actually a sort of secretly sequential product, because actually you're doing Q in this formula here. You're doing QR contraction. You could think of QR as a multi-index and basically flatten these triangles and just think of a matrix and transpose, and that begins to look a lot like the involuted semigroups that we had before, the dagger categories example. Remember, dagger categories in particular, you could think of matrices with transpose or relations with transpose or Hilbert spaces with adjoint and things like that. So it starts to look very much like these examples of semi-heaps that we gave in the beginning. And there is and in fact, I'm currently writing a paper where I'm outlining exactly this point precisely, that you can formally just argue that this is in fact just another case of that. So the fish product, albeit an interesting case and a very important case to discover to sort of motivate us to go further, it is actually not that ternary in a way. I mean, I think the groupoid picture made that case quite explicitly, in my opinion. But then we also discovered it purely for 3 arrays. I mean, there is a formal argument that you can make purely at the level of 3 arrays that tells you that this is actually not that ternary of a product. So the products that are ternary are this so-called Holy Trinity of ternary products, and the reason being particularly perhaps the one at the top left, which is the one that has been actually studied for some time already in the literature, is sometimes called the Zapata-Carratala product. And these involve the triangles in exactly symmetric positions, right? So the difference is that in a fish, you had input, throughput, output kind of structure, or, you're using the fish terminology, you have the tail, the body, and the head, and they are they are involved in different capacities. They all contract different indices, and they are not symmetrically involved in the product. That's in contrast with the usual binary operation of two arrays, which involves two arrays in entirely symmetric conditions, right? So the proper generalization of that situation would be these three topologies. Out of all the possibilities, these are the only three that have that property, that the three triangles are involved symmetrically in the operation. So unfortunately, we don't have, we haven't found non-trivially confluent rewrite systems of hypergraphs with these motifs yet. That's just a problem that we're working on at the moment. And the hope is that by finding those non-trivially confluent rewrites or rewrite systems of hypergraphs, finding those original hypergraphs that will have that property, the hope is that that would lead us to particular algebraic axioms that we might want to claim that are the generalized version of associativity in higher arities. And so the open question still remains: what is ternary or higher associativity? So the difference between this final question and the start of my talk, hopefully, would be that now there seems to be a clear path to follow and to chart out before we can say this doesn't work, because we have good reasons to believe that this non-trivial or dependent confluence property of this hypergraph rewrite systems are a good way to probe into high arity associativity. So that's my part.